All right, this is Module 4, Topic 2, Compound Probability. And so this first lesson is dealing with evens or odds using arrays to organize outcomes. Our learning goals in this are going to be to conduct trials of an experiment, predict the theoretical probability of an event using the results from the trials of an experiment, represent and organize sample spaces for compound events using arrays, lists, and tables. Identify the outcomes in the sample space which compose a compound event. Calculate the experimental and theoretical probabilities of an experiment. Calculate probabilities of multiple outcomes using theoretical probabilities. Use proportional reasoning to predict the probability of random events. You've calculated experimental and theoretical probabilities of simple events. How do you determine the sample space and theoretical probabilities of more complex events? All right, getting started, tossing coins. Suppose you and your partner each flip a coin at the same time. What are the different outcomes that could occur? Use an array, that's what this is right here, to list the possible outcomes of tossing two coins into the air at the same time. Okay. So basically they're saying if myself and my partner both tossed heads, we would have two heads. And then we're just like bringing these together here in the array. And so then it would be and it would be then it would be okay. And so that would be how I'm using the array. I'm bringing them into that spot, kind of like a multiplication table. All right. And then if I'm looking at this, my sample space, use your array to write the sample space for tossing coins at the same time. All right. Well, I could have heads and heads. I could have tails and heads. I could have heads and tails. Or I could have tails and tails. Okay. Now, in the getting started, I'm conducting this experiment for 30 trials and recording the results. Calculate the experimental probability of each outcome in the table. Okay. To help me do this, I will use my random coin flipper here. And if I do that, I'm set to flip two coins 30 times. Click go. And then we have tails and heads. We have heads and tails. We have heads and tails. We have heads and tails. Oops. Tails and tails. Tails and tails. Heads and tails. Tails and tails. Heads and heads. 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 tails and tails, heads and tails, heads and tails, heads and heads, tails and tails, heads and heads, heads and heads, heads and tails, heads and tails, heads and tails, heads and tails, heads and heads, tails and heads, tails and tails, tails and heads, heads and heads, tails and heads, and that was the last one. And so now I look into my totals, and I had 10 that were heads and heads, and then heads and tails were 10, then tails, then heads were 4, and tails were 6. Okay, and then this is 30 times, so that's good. And so if I'm calculating this, this was 10 out of 30. This was 10 out of 30. This was 4 out of 30. And this was 6 out of 30. And I could write all of those as a decimal and a percent. Maybe it'd be good to write these as a percent. This would be about 33% rounded. This would be about 33% rounded. This would be about 13% rounded. And then this would be about 20% rounded. Okay. I don't know if we're going to get to it in the second, but if I'm thinking from the beginning, each of these should be very close to about 25%, because there's 4 main options there. All right. And so I would expect that I would have 1 head and 1 tail when I flipped a coin about 50% of the time, although the order would be different. All right. And so if I look at this, if I add those two up, we would have about 46% of the time that this is the case. Okay. This one's a little high, this one's a little low. And then these two should be right around 50%, because if I add up this and this, that's 50%. And right now that this is at 53%, so this is a little too high. All right. And so now there's a class probability, because what we would do is we would get together and do a whole bunch of groups. And so I'm going to pause this. I'm going to do a couple more groups to add to our results here. Okay. All right. So I just did one more group. And then when I did one more group, I added the results to my results. And so then what we have here would be 16 over 16, which is about 27%. 20 over 16, or 20 over 60, sorry, which is still about 33%. 10 divided by 16, which is about 17%. And then 14 out of 60, which is about 23%. Okay. So if I was thinking about this, let's see here. My theoretical probability for each of these events should be about 25%. Okay. And when I did this here, so this was 8 away, this was 2 away. This was 8 away, this stayed 8 away. This was 12 away, now this is 8 away. This was 5 away, now it's 2 away. Okay. even when we just added one more, we got closer in almost all of the areas to the theoretical probability. Okay? All right, so let's look at our questions on the next page. Combine the results of your experiment with those of your classmates. Then calculate the experimental probability of each outcome and record the class probabilities in the table. Done. We just did two groups, but you could see how it was getting closer. Which probability is more accurate? The probabilities from the experiment with your partner or the class probabilities? The class probabilities. The more trials you conduct, you get closer to the theoretical probability. Use your table to predict the actual probabilities of each outcome. Create a probability model to display your predictions. Okay, so I was kind of talking about this before. I kind of was doing this. We have our outcomes and then we have our probabilities. And with that, we could have heads, could have heads, tails, could have tails, heads, or we could have tails, tails. And each of those should have a 1 in 4 probability, so it's a uniform probability model, okay? But it's not a simple event anymore. Now we're doing two things and makes it more of a complex event, okay? So that was our introduction to this portion. All right, activity 1.1, experimental probability of sums. Joel and Haram, are playing a game using two 6-sided number cubes, so dice. The number cubes are rolled and the sum of the two numbers shown is calculated. If the sum is even, Joel wins. If the sum is odd, Haram wins a point. How can you organize your list to make sure you account for all the possibilities? Okay. Make a list of all possible outcomes when rolling two 6-sided number cubes. So the first one could be a 1, and then the second one could be a 1. And maybe we'll just do all of the ones where it's 1. So the first one's a 1, then it's a 2. First one's a 1, then it's a 3. First one's a 1, then it's a 4. First one's a 1, then it's a 5. First one's a 1, then it's a 6. Okay? And that's all the possibilities if the first dice we roll is a 1. Then, if we look at this, then we pretend it's a 2, and the other one's a 1. 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. All right. See the pattern? This is a big sample space. Okay. Getting there. And last. Okay, so this would be all of our possible outcomes we could, or what we would roll, or what we could roll. All right, then create a sample space for the possible sums in the game. Well, let's just look. This should be pretty quick. 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. 7, 8, 9, 10, 11, 12. Okay. Nice little pattern we got going on there. All right. But I'm noticing here that my smallest sum was 2. And so the sample space would include 2 all the way up to 12. Okay. Do you think each of the outcomes in the sample space is equally likely? Explain your reasoning. No. You see why? Like I can tell just by looking at, I see that there's only 1, 2, and there's only 1, 12. So I can see that some have more than others. So I can see that some outcomes occur more than others. So that would be like a non-uniform, right? Probability model, right? Predict who has a better chance of winning this game. Explain your reasoning. Well, initially, my first prediction is, let's see here. Sum's even, Joel wins. So I think it's Haram. Haram has a better chance of winning because 2 even numbers appear only once. Okay. And so that's my prediction. So if I just looked quickly, I saw that 2 only appears one time on my whole list, and like 12 only appears one time on my whole list. Okay. All right. Play the game 25 times with the partner. List each possible outcome in the first column. Tally your results in the second column. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Advanced counting with Molnar. All right. Then tally my responses. So random number roller here. 2 dice, 6-sided, 25 times. Click roll now. Hopefully. There we go. All right. Then let's see here. We have 8, 8, 9, 6, 11, 8, 4, 3, 6, 7, 4, 4, 2, 7, 4, 7, 7, 9, 7, 9, 6, 3, 6, 2, and 10. Okay. All right. Then if I take a look here, list each possible outcome in the first column, tally your results in the second column, done. Calculate the experimental probability for each outcome, express each probability as a fraction and as a percent. Record your probabilities in the third column of the table. 2 out of 25 times 4 would be 8%. 2 out of 25 times 4 is 8%. 4 out of 25 times 4 is 16%. 0 out of 25 times 4 is 0%. 4 out of 25 times 4 is 16%. 5 out of 25 times 4 is 20%. 3 out of 25 times 4 is 12%. 3 out of 25 times 4 is 12%. 1 out of 25 times 4 is 4%. 1 out of 25 times 4 is 4%. 0 out of 25 times 4 is 0%. Okay, done. Okay, according to your experiment, who would win the game between Joel and Hiram? Explain your reasoning. Okay, so let me see here. If I've got this right, Joel is even. Hiram is odd. Then if I look at this carefully, even would have occurred 2 out of 25 plus 4 out of 25 plus 4 out of 25 plus 3 out of 25 plus 1 out of 25. Okay. Odd would have occurred 2 out of 25 plus 0 plus 5 out of 25 plus 3 out of 25 plus 1 out of 25. Okay. When I figure that out, we have 2, 6, 10, 13, 14, 14 out of 25. According to this, we have 7, 10, 11 out of 25. Does the outcome of the game match your prediction of the winner? Explain your reasoning. No. I believe we would have to do more trials. Okay. Last, suppose you wanted to calculate the theoretical probability of each sum. Explain how you might proceed. Well, I would do what I started to do. Find the sums of all the outcomes. Then write each sum as A probability. Make a table. So let me explain. Make a plan, but do not carry it out. You will calculate the theoretical probabilities of this experiment in the next activity. Okay? So I'm going to use what I started to do here where I have all the sums to help me. And so we're going to do this in the next activity, which we're going to cover tomorrow. All right. But that's the end of the intro and of activity 1.1, where we're starting to look at compound probability, which is more than one. All right. We're doing simple probability, which is just one thing. And that is our lesson for today.